Hey, this is Charlie Thompson, and welcome to the pre-lab video for Lab 6 on humidity. So here are the learning objectives for this lab. You should be able to find specific humidity, and for the lecture slides for this, I've made hyperlinks out of all of the important parts, the important learning objectives. So if you want to go right to the find specific humidity part of the lecture slides to go over my walkthrough of how you find specific humidity, I've made handy dandy links so you don't have to look back and forth through all the slides. So back to the learning objectives: find specific humidity, find maximum specific humidity, find dew point temperature, calculate relative humidity, and enter numbers into Canvas. That's just rounding, and I go over everything you need to know. There's a cheat sheet to hand out, and I also go over it in this video. So what's up next? Definitions. There's a ton of definitions, and there's no way around that, so let's go through those. There's a cheat sheet that I've made, the handout. It'll have definitions. It'll give you instructions on what to do and how to do it, and also practice problems and their answers. So you can do some practice problems to see if you understand how to do it before you actually have to do anything for a grade. So definitions: humidity, saturation, dew point temperature, specific humidity, maximum specific humidity, relative humidity. So humidity is just referring to water vapor in the air. Water vapor is a gas. It is water that has evaporated because it has absorbed enough heat energy to go through a phase change. It's no longer liquid. Now it's a gas. The amount of water vapor that can evaporate depends on the temperature. Since heat energy evaporates water, the higher the temperature, the more heat energy there is, the more water can evaporate. If you're in a desert, if you're in Las Vegas, it doesn't matter how much heat energy there is. If there's no water, it can't evaporate. So, like I said, higher temperature, there is more energy available to evaporate water. Doesn't mean that you necessarily have that water, but there's the potential to evaporate water. Yeah, I'm just going to back all those up. So humidity is referring to water vapor in the air. It is a function of temperature. The higher the temperature, the more energy there is available to evaporate water. Water is evaporated by liquid water absorbing heat energy and then undergoing a phase change and becoming a gas. So the more heat energy there is available, the easier it is for water to evaporate. The more water can evaporate. It doesn't mean that there is more water vapor. It just means that there could be more water vapor. If you're in like Las Vegas where the relative humidity or there is no water to evaporate, it doesn't matter how much heat energy there is, there's no water to evaporate. So I'll talk about the difference between specific humidity, which is what you have, and maximum specific humidity, which is like potential humidity. Saturation is an important concept. When the relative humidity is 100%, we say the air is saturated. All the energy to evaporate water has been used up. So it is impossible to add more water vapor to the atmosphere at that point once it's saturated. If you add water or if you cool it, you'll get condensation. The dew point temperature is the temperature at which a given mass of air becomes saturated and condensation begins. So as a parcel or blob or cloud-sized blob of air cools down, once it cools to dew point, the relative humidity is 100%. That parcel is saturated. And we're going to abbreviate that TDP for temperature dew point or dew point temperature. I might be a little inconsistent on the capitalization, so capital D, lowercase dp, or all caps, doesn't matter. It's the same thing. TDP is the dew point temperature. If it's below zero, we call it the frost point. We probably won't deal with any problems like that, though. Okay, specific humidity versus maximum specific humidity. So specific humidity is just how much water vapor is present in the air. It is expressed in mass of water vapor in grams of water vapor per kilogram of air. 1 cubic centimeter of water is 1 gram. So 1 cc is about the volume of a sugar cube. So if you imagine a sugar cube's volume's worth of water, that would weigh 1 gram. That's what 1 gram of liquid water looks like. 1,000 cubic centimeters are 1,000 grams, or a kilogram, or a liter. A liter of water weighs 1 kilogram. So if you have a quart water bottle, that weighs about 1,000 grams. And finally, 1 kilogram of air has a volume of about 1 cubic meter. So if you imagine a blob of air, a floating cube of air, about 3 feet by 3 feet by 3 feet, that weighs about a kilogram. So to give you some idea of the volume of air that we're talking about when we're talking about a cubic meter of air or a kilogram of air, it's about 3 feet by 3 feet by 3 feet. So as an example of how we express specific humidity, 10.6 grams per kilogram would be an example. The maximum specific humidity is how much water vapor could be present at a given temperature. It's just a function of temperature. It is a potential humidity. It's just looking at the energy available to evaporate water. So maximum specific humidity is the amount of water vapor that could be possible. And it doubles every time the temperature increases by 10 Celsius degrees. At 0 degrees, the most you can have is about 4 grams of water vapor. At 10, you could have 8 grams of water vapor. At 20 degrees, you could have about 15 grams of water vapor. At 30 degrees Celsius, you could have about 27 grams of water vapor. And finally, once you get up to 40 degrees Celsius, you could have 47 grams of water vapor, which is just about 2 ounces of water. It's a quarter cup of water per cubic meter. That's a lot of water vapor. On this chart, the way you find the maximum specific humidity, if you know the temperature, for example, 20 degrees, you go up and then over to the left. So at 20 degrees, it looks like these are in grams, so that's 10 grams, that's 20 grams. Looks like about 15 grams. And we're going to use this chart, a little bit more accurate. At 20 degrees, it looks like the maximum specific humidity is 14.7 grams. So you find the temperature, slide over to the left, and that's what the maximum specific humidity is in grams. It doesn't tell you what the specific humidity actually is. It just tells you how much it could be. Dew point temperature. So to find dew point temperature, if you know the temperature, you know what the maximum specific humidity is. If you know what the maximum specific humidity is, you know what the dew point temperature is. So if you know one, you know the other. And we're just going to use this chart. This is an example. You'll have a different chart. So, for example, if I told you that this parcel of air has 10.6 grams of water vapor per kilogram of air and asked you what the dew point temperature is, you'd look it up on the chart, find 10.6. There it is. Slide over to the left. And the dew point temperature is 59.0 degrees Fahrenheit. If you know the dew point temperature, you can find the maximum specific humidity. So if I told you the dew point temperature was 32.0 degrees Fahrenheit, you find that temperature on the chart, slide to the right, and there's your answer. 3.8 grams of water per kilogram of air is the maximum specific humidity at 32 degrees Fahrenheit. So to find the dew point, again, you read the maximum specific humidity and then go left to find the dew point temperature. But sometimes your maximum specific humidity will be in between the values on the chart. In that case, what you're going to do is use the cooler temperature. Like if I said the specific humidity, the actual specific humidity, this chart works for both. Like if you know what the specific humidity is, you look it up, slide to the left, and that's your dew point temperature. So if your specific humidity was 5 grams per kilogram, you can see that's less than 5, but more than 4.8. So the dew point would actually be someplace around 38 degrees. You wouldn't get condensation at 39 degrees because we have less than 5 grams of water vapor. You for sure would have condensation when it cools to 37 degrees because we have more than 4.8 grams. So for this class, we're just going to use the cooler value. So if I told you that the specific humidity was 5 grams per kilogram, the correct answer for the dew point temperature would be the cooler of the temperature is 37.4, because by that point you definitely would have condensation. Relative humidity tells you how much humidity you have compared to how much you could have, relative to how much you could have. So the formula is the amount of water vapor present, which is the specific humidity, divided by the amount possible, which is the maximum specific humidity. The amount present, how much you have, amount possible is a function of temperature. It's just the max specific humidity off the table. So, for example, if it was 5 o'clock in the morning and 0 degrees, the specific humidity is 4 grams. That's what we have. The maximum is also 4 grams. 4 over 4 is 100%. So the relative humidity is 100%. The air is saturated. Dew point temperature is 0 degrees. If it gets warmer by 10 degrees, the maximum increases to 8 grams. The amount present is still 4. We don't get more water vapor as the air warms. A good way to think of this is just go back to Las Vegas. If the air warms up, there's no water vapor, so you can't have more water vapor. You won't get more water vapor until that air moves someplace where there's water or vegetation, something giving off evapotranspiration, giving off water. So an important thing to remember is the maximum specific humidity increases as temperature increases, but the specific humidity doesn't. That's how much you have, and it doesn't necessarily increase if the temperature increases. In fact, just assume it doesn't. So if it's warmer by 10 degrees, we still have 4. The max is now 8. 4 over 8 is 50%, and the relative humidity is therefore 50%. If it gets warmer by another 10 degrees, up to 20 degrees, the maximum doubles again, this time to 16 grams. So you can look it up on the chart. It's not exactly 16, but it makes the math work out okay for this example. For everything you'll be doing, you'll have to use the chart and get the exact answers. But if it warmed up to 20 degrees, we still have 4 grams. The maximum specific humidity is 16 grams, so 4 over 16 is 25%. The relative humidity has fallen to 25%. So as it warms, if the temperature increases but the specific humidity stays the same, the relative humidity is going to decrease. If the air gets warmer, the relative humidity goes down. If the air gets colder, the relative humidity goes up. So if it's 32 degrees Fahrenheit and we've got 3.8 grams and the temperature increases to 68 degrees and we still have 3.8 grams, you can see that the relative humidity now is going to be roughly 25%. It was 100%. We had 3.8. That was the max. So at 32 degrees, the relative humidity would have been about 100%. If it increases to 68 degrees, the relative humidity is now roughly 25%. We have 3.8. The max is 14.7. So we've got about 25% relative humidity. The same thing happens as air cools. So at 35 degrees Celsius, let's just say it's 35 Celsius, and we've got 36.4 grams per kilogram. The air is saturated. What's going to happen is, as the air cools, the maximum is going to decrease, and it's impossible to have more than the maximum in the air. What happens as the maximum gets lower than how much you have is you'll get condensation. So in this case, if the air cools by 15 degrees down to 20 degrees Celsius, we had 36.4 grams per kilogram, and now the max is 14.7. So we started with 36.4, we now have 14.7. 21.7 grams of water vapor would have condensed out because the new maximum is 14.7. That's all you can have. Anything over that is going to condense out. So if the specific humidity remains the same, but the temperature goes up, the relative humidity goes down. So this is showing temperature. This is showing relative humidity from the Sacramento airport. You can see the temperature goes up, the relative humidity goes down. When the temperature goes down, temperature's gone down, the relative humidity goes up. So they're inverse. There's two instruments used for measuring humidity, two relatively common. One's a sling psychrometer. It has two bulbs. There's a wet bulb and a dry bulb, and you spin it around, and as water absorbs heat and evaporates, it takes the heat with it, cooling the wet bulb. So as water absorbs heat and evaporates, it cools this thermometer. If there's no difference in temperature, and if there's no evaporation, there's no cooling. If there's no difference in temperature, that the air that you're measuring, the air that you're sampling, is at 100% relative humidity. If there's no temperature difference, then the relative humidity would be 100%. If there's a big difference, that means lots of water vapor evaporated. Lots of water evaporated means the air is relatively dry and the relative humidity is low. There's a table that you'd look that up on. You look up the wet bulb temperature, the dry bulb temperature, and then what the difference is between them. And then the chart just shows you what the relative humidity actually is. The other instrument is called a hair hygrometer, and it actually uses strands of human hair. As the hair absorbs moisture, it contracts, which then pulls the needle up. When the hair gets dry, it stretches out, and so the needle drops down, which is, I think, a really weird way of measuring humidity. So let's talk about calculating different types of humidity. So for specific humidity, that's just how much you have. Relative humidity is how much you have compared to the maximum. Temperature, dew point, temperature, we need to know those. Relative humidity, we'll be calculating that. Specific humidity, we'll also be calculating that from relative. So relative humidity equals the amount of water vapor we have compared to the amount of water vapor possible. Amount present is how much you have. The amount possible is a function of temperature. So to find maximum specific humidity given a temperature, we'll do that, and then we'll also find the dew point temperature given a specific humidity. We will also calculate relative humidity given a specific humidity and an air temperature. So there's a lot of different things we can do. We can also calculate the specific humidity given the relative humidity and a temperature. So to find the max specific humidity, if you're given a temperature, you find the temperature in the chart, and then you slide over to the right, and that is the maximum at that temperature. So if I told you the air parcel is 77.0 degrees in temperature, what's the maximum specific humidity? You just look it up and say, oh, it's 20.0 grams per kilogram. To find the relative humidity, which is the amount of water vapor present compared to the amount of water vapor possible, here's the example, the way I'll set up the problem. I'll say it's 77 degrees. We've got 10 grams of water vapor. That is the specific humidity. We look it up on the chart. At 77 degrees, the maximum is 20 grams of water vapor. 10 over 20 is 0.5. Multiply that by 100 because we express relative humidity as a percent. So that's 50%. And for the rounding for all of the percent, the relative humidity, we're just rounding it to a whole number. So 50%, if you get like, whatever, 49.5, let's make it easy, 49.9, just round it to 50. For the relative humidity, round it to a whole number. So finding specific humidity, that's how many grams of water vapor we have. If you know the relative humidity and the temperature, the relative is like what fraction of all the humidity is actually present. So we can look up, if we know what the temperature is, we can look up what the max is. And then the relative is a percentage of the max. So we know the relative humidity and the temperature. It's 77 degrees with 50% relative humidity. So what's the specific humidity? Well, we have to look up and find what the max is. The max is 20 grams at 77 degrees. So we know it's 77 degrees with 50% relative humidity. That means we have 50% of the maximum. The max is 20. We have 50% of that. 20 times 0.5 is 10 grams of water vapor. So the specific humidity is 10 grams. 50% of 20 grams is 10 grams. A few more notes about relative humidity, specific humidity, and dew point temperature. If you know 2, you can find the third. So specific, if you know the temperature and the relative humidity, you know what the max is. If you know the temperature, you know what the max is. You look it up on the chart, and then you can find what the specific humidity is. So maximum specific humidity, how many grams are possible at that temperature, times the fraction of the total that you have, gives you the specific humidity. So the last example we did, the max is 10 grams, or I guess this is a new one. Max is 10 grams. The relative humidity is 50%. So if I told you the temperature, you'd look up the max on the chart. The max is 10 grams. The relative humidity is 50%. So the specific is 5 grams. If you're given the dew point temperature, 77 degrees, you know what the specific humidity is from the chart. If you know what the dew point temperature is, you can find the specific humidity on the chart. Find the dew point, slide over to the right to find the specific humidity. That's it. Dew point temperature, you can find the dew point by using the chart of maximum specific humidity. The actual dew point temperature will probably be between 2 temperatures. Use the lower, since condensation won't begin until it cools to the lower temperature. So, for example, I find the specific humidity is 7 grams per kilogram. So if I gave you this in a problem, given a parcel of air with a specific humidity of 7 grams, what is the dew point? You'd look it up on the chart. The maximum, if you had 7.2 grams, the temperature, the dew point would be 48 degrees, 48.2. If we had 6.7, it would be 46.4. We have 7 grams, so we're going to use the cooler temperature of 46.4 as the dew point temperature. So it won't be the 48.2 because we have only 7 grams, so you won't get condensation when it cools down to 48.2. When it cools down to 46.4, there will definitely be condensation. So 46.4 would be the number that we'll use as the dew point temperature given 7 grams of water vapor per kilogram of air. So again, dew point temperature with 7 grams is 46.4 degrees Fahrenheit. You can calculate the specific humidity and then use the specific humidity to find dew point temperature. So you find the dew point temperature by using the chart of maximum specific humidity. If the dew point's between 2 temperatures, we're going to use the cooler temperature. So given specific humidity is 5 grams, what's the dew point? So the chart shows the maximum. If we had 5.1 grams, is 39.2. If we had 4.8 grams, it's 37.4. So 5 is between them. So we're going to use 37.4 degrees as the dew point temperature given 5 grams of water vapor per kilogram of air. Relative humidity. If you know the temperature and the specific humidity, you know the dew point temperature from the chart, and then you can find the relative humidity. Specific humidity divided by the max specific humidity equals relative humidity. Well, actually, specific divided by the max times 100 is relative humidity. So if you were given that the specific humidity is 5 grams and the max is 10, then the relative humidity is 50%. If you know the temperature and the dew point temperature, then from the chart, if you know the dew point temperature, you know what the specific humidity is. If you know the temperature, you know what the max is, and then you can find relative humidity. So again, specific divided by max specific is relative humidity. Specific divided by max specific times 100 is relative humidity. So if we've got 5 grams and the max is 10, relative is 50%. So you can find relative humidity if you know the temperature and the dew point temperature. Then we can look up on the chart to find the specific humidity. Once we know the specific humidity, we can find the dew point temperature. If we know the temperature, we know the max specific humidity. Relative equals specific humidity divided by max specific humidity times 100, expressed as a whole number %. When you enter numbers in Canvas, temperature, dew point temperature, specific humidity, max specific humidity, all of those we're going to round to 1 decimal place. 7.8. There's a bug in Canvas. If you get something that's like 10.0, 1.0, anything 0.0, you can't actually enter the 0.0, so don't worry about it. Relative humidity, round to a whole number. So both of the temperatures, temperature and dew point, and both of the specific humidities, specific and max specific, round to 1 decimal place. Relative humidity, round to a whole number. If you found 33 is the answer, if you found 33 is the answer, that's going to be 33%. So temperature, dew point temperature, round to 1 decimal place, like 75.2 degrees. Specific humidity, round to 1 decimal place, 7.2 grams. Max specific humidity, round to 1 decimal place, like 8.4 grams. And relative humidity, round to a whole number, like 33%. That's it for Lab 6. If you have any questions, please give me a call, text me, email me, whatever. This is another lab that 5 minutes conversation can open up the whole lab for you and make it easy. I wish you good luck on Lab 6. I hope you enjoy it.